So with our motivation in mind, we'll talk about our measures of variation, where the first one we have is the range. And we already talked about the range. It's just the highest value minus the lowest value. It's not a very interesting computation, but it can tell us something quickly about the spread of our debt. That, for example, looking at the batteries, the battery 1 has a highest value of 24 and a lowest of 4, so it has a range of 20 hours, while battery 2 has a highest value of 18 and a lowest of 10, which would give a range of 8 hours. Tells you that battery 1 is, in a sense, more consistent, exactly like we'd expect. Quick computation doesn't tell us a ton, but it gives us a bit more context, which is what we're looking for here. And we probably still want more. So then we'll build towards an idea called standard deviation. And this is really the most important thing in this entire section. But to understand what standard deviation is, we have to start with an idea called deviation, where a deviation is just a distance away from the mean. So it's some value x minus the mean, whether that's x bar or mu. It's just how far away something is. So if the mean is 4 and the value you're comparing it to is 8, you have a deviation of 4. Or if the value was 0 and the mean was still 4, you'd have a deviation of -4. It's just how far away the value is, either above or below from the middle. And that seems like the nice sort of thing to think about in the context of spread. So it makes sense to want to talk about something like an average deviation, and there is something called a mean deviation, but we very rarely look at it. Not entirely sure why, though. Anyway, we instead look at what's called the standard deviation, which is its own sort of average deviation. It's just got a little bit uglier of a formula than what we normally got from averages, or at least what we got from averages in the last section, where to get the standard deviation, what you do actually changes a little bit whether you're talking about a sample or a population. For a sample, you take your deviations, square them, and add up the squared differences, then divide the squared differences by 1 minus the sample size, and take the square root of that whole mess. Meanwhile, for a population, you do the same sort of thing with sums of squared differences, but then you divide by the entire population size, not the population size minus 1, and then take the square root. Where for samples, we call it S, and for populations, we call it sigma. And there, at least to me, is a somewhat intuitive reason for why S has a different formula than sigma, and it's because when we're talking about a sample versus a population, we should always leave the door open for a little bit of extra variability. For the fact that we're not getting all of the information in the population, we're just taking some of it. And because we're just taking some of it, and this is specifically meant to measure variability, the sample should be a little bit bigger. So we make the denominator in the formula a little bit smaller, makes the whole thing a bit bigger. Long and short of it is, whenever you're looking at this kind of computation, you'll notice, or at least you'll begin to notice with practice, that S is always larger than sigma. And then from there, we can talk about variance, which is the square of standard deviation. And when you're going to compute this stuff by hand, you usually get the variance first. But an interesting thing happens with all of these squares and square roots, that the variance is kind of a unitless measurement. It's a measurement of square things, whereas the standard deviation specifically looks at things in terms of the unit that we're originally talking about. So really, when we're talking about running these kind of measures of variation, number one with a bullet is the standard deviation. But that's kind of a nasty formula. And computing it by hand is somewhere between incredibly clunky and time consuming, and just short of impossible if you don't get lucky with perfect squares. Really, in my opinion, computing standard deviation by hand is the sort of a thing you might do once to prove a point, but I don't care if you do this by hand. I'm not going to show you a worked example for doing this by hand. I don't expect you to do it by hand. You've got better uses of your time. Instead, when we talk about this stuff, even though it is kind of important to understand this formula here, specifically this difference between the two formulas, I'm going to focus on how you do it in the calculator. But that's what we'll see next.